So in this question already there is mass is there in the balance. There's already some sand is there in the balance. Then we'll find how much sand will enter. And because what happened, as the sand particles are moving, they will hit the container. So as these sand particles will hit, so there will be a change in momentum. So as there is a change, because these sand particle as if hit this, so there will be a change in momentum. And that change in momentum will also cause a force. So there is a downward force because of change in momentum. There is a downward force due to the weight, and there is a downward force due to the weight of the container. So three downward forces are there. One is the weight of the container. One is the force due to change in momentum of the sand. Another one is the weight of the sand. So these are the three downward force. So you already know the original mass, you know the rate of the flow, like how much mass. Zero point 0.3 can flow per second. So 10 second multiply, you will get 3. And originally the mass was 0.65. So 3 plus 0.65, that will be 3.65. But what happened, there is another force is there, and that force is due to change in the momentum. Because it is moving, it hit, and as it hit, there will be a change in the momentum. And using this change in momentum, the final will be 0. Initial, how much mass is coming per second? So 0.3 is there, multiplied with what speed it is moving. 0.3 into 5.6. What's the answer? 0.3 into 5.6. That is 1.68. Because what happened, the sand particles are moving and they stop. So there is a change in momentum. So due to change in momentum, these sand particles will apply downward force. The container is already applying a downward force, and sand, there's a weight of the sand which is also acting down. So how to calculate this force? That is a change in the momentum. So mv minus mu, final momentum is 0. Initial momentum, the mass is there, which is 0.3 per second is there. So time is 1 second multiplied by velocity at which it was moving, that was 5.6. So when you multiply 0.3 with 5.6, you will get 1.68. So 1.68 is this force, which is, but this is the force, you need the mass. So how much matter it appear, contribute. So you will use F is equals to ma and find this mass. And this expression will be due to gravity. So F divided by A will be m. Is it clear? Then 21C. So in 21C, this is about the rate of the flow. Because it is moving at a constant rate and already some mass is there. So there is some mass is there. That is the mass of the container. That is why it is a horizontal line. But what happened when time is equals to 5 seconds is the time at which the sand start to land. So as the sand start to land, the mass will start to increase, but it is increasing with a constant rate. So it will increase until 30 seconds. Is it clear? So why there is no change in the mass? Because already so this is question 21C I'm discussing now. And then practically what happened, as we know, because in this case, what is happening? The downward forces, there is a weight of the container, there is a weight of the sand, and there is a force due to the sand because of change in momentum. Okay. So that force is there, but when the sand start to, like when all of the sand is transferred from the funnel to the container, this force will be zero. Why this force is zero? Because now there is no change in momentum. So when this force is no longer there, the weight or the downward force start to or appear that it decreases. So that is why it was starting first with some value, because that was the mass of the container. So at 25, the sand stopped landing. So this is the point where the sand stopped landing. If there is no more sand landing now, so there is no change in momentum. So that force will no longer be there. So the downward force on the balance will be smaller. So that is why you will have a smaller reading from 25 to 30, because there is no change in the momentum. So there is no change in that, force is not contributing. Is it clear why this downward step is there? Is it clear, this part? So example, if I say weight of the container is 5 newtons. That is downward. So example, this was in Newton, it is in, so it was 5 Newton. Or otherwise you will be confused. Example, it was 15 Newton. So 15 Newton, it will be constant. Now we are adding a sand. So when we are adding a sand, so there is a weight of the sand that is increasing continuously. And because when the sand is hitting this container, there is a change in momentum of the sand. And due to this change in momentum of the sand is applying another force. Say example, this was 5 Newton force. So what is the total downward force? 15 Newton, the weight of the container, 5 Newton due to change in momentum of the sand, and weight of the sand which is continuously increasing. That is why the two forces are not changing. Weight of the container is not changing, and the force due to change in momentum, because every time the same amount of sand is moving with the same speed. That's why there's no change in momentum. Or there is constant force. There is a change in momentum with a constant force. And amount of sand is increasing. That's why the weight of the sand is in. Once all of the sand is being transferred, so if all of the sand added to this container, now this 5 Newton force was due to the change in the momentum of the sand. So now this 5 Newton will no longer be there. So if this 5 Newton is not there, what will happen? The weight of the container, basically the downward force, will decrease. Is it clear? This part? In the beginning, there was, because the sand was not moving, so that force was not contributing anything. That was only the weight of the container. But when the sand is added to a container, there is a change in momentum that causes a force, downward force. And there is already weight of a sand is also, because the amount of sand in the container is increasing. So it is, and its weight is increasing with a constant rate. But once all of the sand is being transferred, then the change in the momentum is not there. So that downward force is not there. That is why the weight, the downward force appear to decrease. So this was question 21, part C. Then question 22, which part State two quantities that are conserved in elastic collision. In elastic collision, when the collision is elastic, both momentum and kinetic energies are conserved. The definition of elastic collision means momentum and kinetic energy conserved. If you mention a total energy is there because it is according to law of conservation of momentum, law of conservation of energy, that energy cannot be created nor be destroyed, changes from one form to another. So it cannot be against the law of conservation of energy. So that's why total energy is not the answer here. It should be kinetic energy. It is obvious that the total energy will be conserved, but specifically which form of energy is conserved in the elastic collision, the kinetic energy is conserved in the elastic collision. Specific. Then page 19, question 24. A deep space probe often carry a module which may be ejected from them by explosion. A space probe of total mass of 500 kilogram is traveling in a straight line through a free space at 160 meter per second. When it ejects the capsule, the mass of mass 150 kilogram explosively, releasing energy immediately after the explosion. The probe now has a mass of 350, continued in the original straight line but travel at 340 as shown. Discuss how the principle of conservation of momentum and conservation of energy apply in this instant. The quality of your written communication will be assessed in this question. So basically, look, first thing, the momentum before collision should be equal to momentum after collision. For a conservation of the momentum. So what is the initial or direction of the initial momentum? The direction of the initial momentum is towards right hand side. So what should be the direction of the final resultant momentum? That should also be towards right hand side. So what happened when there is an explosion? As the capsule is moving backward, you can see the speed of the probe increases. Why the speed of the probe increases? Because what we want the resultant momentum towards right hand. Before explosion, momentum is towards right. So after explosion, the resultant momentum should be towards right hand side as well. So what happened as the capsule move backward? So to have the same resultant moment towards right hand side, the probe should move with a higher speed. The probe should move with a higher speed to have a resultant momentum towards right hand side. This is in terms of conservation of momentum. Then what about the conservation of energy? When you compare the conservation of the energy, so energy cannot be created. First thing, you will write a law of conservation of energy. Energy cannot be created nor be destroyed, but changes from one form to another. So explosion, explosive, there will be an initial chemical energy, and that chemical energy transformed into kinetic, heat, and light energy. Is it clear? So basically, you have to mention the conservations of the energy and the conservation of momentum. So first thing you will mention, according to law of conservation of momentum, momentum before should be equal to momentum after. So in this example, the initial momentum is towards right hand side. So the final momentum should also be towards the right hand side. But when there is explosion, if a capsule is moving in opposite direction to the probe, then probe should move with a higher speed so that the resultant momentum is towards right hand side. And that is obvious from the figure. You can see initially the probe was moving with 150, 160, but later it is moving with 240. So that shows that higher momentum for a probe after, because it need a resultant momentum towards right hand side. And in terms of energy, you will first mention a conservation or law of conservation of energy. Energy cannot be created nor be destroyed, changes from one form to another. And then mention what are the energy changes here with respect to the example. Calculate the magnitude and the velocity. Calculate the magnitude of the velocity of capsule immediately after the explosion and state the direction of the movement. Look, we will consider it move in and we will consider it is moving in opposite direction. If we are getting a positive answer, it means our assumption was right. If we are getting a negative answer, it means our assumption was wrong. It is moving in opposite what we assumed. So when we apply a conservation here for momentum, so momentum before collision is equals to momentum after collision. In the beginning, both like a capsule and probe are together as one object and both are moving with the same speed because a capsule is inside the probe. So the momentum before should be equal to momentum after. So what is the momentum before? The momentum before you can work out in this manner, like you can consider a capsule will be 150 into 160 plus the probe will be 350 into 160. Or you can directly, because it's one body in the beginning, so you can take the total mass as 500. So total mass is 500 multiplied by velocity 160. Then the mass of the capsule is 150 and it is moving with velocity v, but what we consider, example, we consider it is moving in opposite direction of the probe. So I'll not take as v, I will take as minus v. So the momentum will be opposite. Plus this will be 350 multiplied by 240. So when we solve this, 500 into 160 minus 350 into 240 and then divided by minus 150. So what's the final answer when 500 multiplied by 160 minus, because this whole factor, 350 into 240 divided by minus 150. So what's the final answer for the velocity? When you work out, what's the final answer? 26.67 or 26.7. Three significant figure. So our final answer is positive. It means the direction which we consider for the probe, that is the correct direction. That's why we are getting a positive answer. In the next part, the direction of the movement is towards the left hand side because we consider it is moving towards left and we are getting our positive velocity. It shows that our assumption was correct. Determine the amount of energy given to the probe and the capsule by the explosion. So basically, look, originally there is a kinetic energy. Originally there is a kinetic energy. Then you'll find, as we worked out, the kinetic energy is a scalar quantity, so it does not depend on the direction. It's a scalar quantity. It was moving with 26.7 meter per second. So find the kinetic energy of the capsule and kinetic energy of the probe. So originally there was a kinetic energy, and final kinetic energy is a sum of kinetic energy of the capsule plus probe. And when we take a difference of these two energies, the, the final kinetic energy minus the initial kinetic energy, we will know how much energy is supplied by the explosion due to a chemical reaction. So you will use the formula kinetic energy half mv square, find the initial kinetic energy. You will find the kinetic energy of the capsule and kinetic energy of the probe, add them, that will be the final kinetic energy. Subtract the two kinetic energies to identify how much energy is provided by the explosion. Like example, if I say this was 100 joules, this was 3 joules, this was 7, or this was 170 joules. So what is the kinetic energy provided by the explosion? Originally it was 100, but now it is 173. So it will be 173 minus 100. So 73 joule of energy they get due to explosion. So same thing, you will find the kinetic energy before and after. The kinetic energy after is the sum of the kinetic energy of capsule and probe, and initial is only for the whole object, and subtract the two energies to find how much energy is supplied due to explosion. Is it clear? This part? So any other question or a doubt? 25 part C. Page number 21. This is page 21. Discuss the consequences if the ball had approached the board at a higher speed but still received the same impulse. So basically what happened? In the question, a football of mass 0.42 kilogram moving horizontally at 10 meter per second toward a footballer's boot, which then kicked. The figure below shows how the force between the boot and the ball varies with time while they are in contact. And discuss the consequences if the ball had approaches a boot at a higher speed but still receive the same impulse. So in the beginning, in this question, I guess the ball was moving horizontally at 10 towards the footballer. But now they're saying a ball is moving at a higher speed and it is moving towards the footballer. But the impulse is the same. So what might happen? Because you have the formula, impulse is equals to change in momentum. It's mv minus mu. So what you want this to be constant. You don't want the impulse to change. But what happened? The initial velocity change. If the initial velocity change to have the same impulse, what should happen? The final velocity should also change. Because I need the same difference. Like example, if I say the final momentum was 10 and initial momentum was 2, so the difference in the momentum is, or impulse is 8 Newton second. But if the final momentum, initial momentum I made 20, what should be the final momentum so that I have the same impulse, same change in momentum? So what should be the final momentum? It should be 28. So the initial momentum will be higher. So what the change in the momentum, when we want to change the momentum, so what we need, if we want the same change in momentum or the difference in the two momentum, the final speed should be higher. And if we want a greater final speed, so we should apply a greater force to have the same change in momentum. Is it clear? So these are the questions related to momentum. Any question or doubt? Still, any doubt is there in this topic of momentum? Is there any doubt?